first three sections of Chapter 14 deal with trig identities. So you need to know the basic trig identities, which I'll go over in a minute here. Simplify trig expressions using trig identities. Solve trig equations, so when you have to think about the quadrants. Write reciprocal trig ratios, so know how to write a ratio for sine, cosine, tangent, cotangent, secant, and cosecant. And also just go back to the basic using SOHCAHTOA. So when verifying trig identities, one technique that you can do is start on the side that looks more complicated. So I could take this part and rewrite it using sine and cosine and end up over here. That's one way you can do it. So I'm going to do it that way first. So I have secant is 1 over cosine of x minus tangent of x, which is sine of x, over cosine of x, times sine of x, which is going to be my numerator. So right now I have a common denominator. Right here I have cosine of x, so I can combine the numerator to be 1 minus sine squared x over cosine of x. So the Pythagorean identity is, one of them is cosine squared x plus sine squared x equals 1. So right here, if I subtract cosine squared of x from each side, I'm going to have 1 minus sine squared x equals cosine squared x. So 1 minus sine squared x is equal to cosine squared x. So now I have cosine squared x over cosine x, which equals cosine x. Now, cosine of x is the reciprocal of 1 over secant of x. So therefore, this is equal to 1 over the secant of x. Now, maybe what you can do is you could also think of 1 over secant of x as 1 over cosine of x. So this would just be cosine of x. So if that's easier to think of it that way, then you could stop right here. So you could simplify this side and write this is cosine of x, and then end up getting cosine x over here. And then number 2 is I'm going to show you I could do something different right here. I'm going to multiply both sides by sine of x. So this is going to be 1 plus cosine x equals cosecant x times sine of x plus cotangent x times sine of x. So sometimes you could write it out in terms of sine and cosine. This time I'm just showing you a different method. Then I'm going to multiply both sides by sine of x just to get rid of the fraction. So now the left-hand side is still 1 plus cosine x. Now let's work with this right side here and write in terms of sine and cosine. So cosecant of x is 1 over sine of x. Sine of x is still sine of x. Plus cotangent, which is cosine of x over sine of x. And then sine of x is still sine of x. So my left-hand side is 1 plus cosine of x. And my right-hand side is, these two cancel out, so I have 1 plus, these two cancel out, cosine of x. So the left-hand side equals the right-hand side, so I've verified it. You can also simplify using trig identities. So notice how there's not a right-hand side and a left-hand side of the equation. So sine theta over cosecant of theta is 1 over sine of theta plus cosine of theta over secant is 1 over cosine of theta. So when you have fractions, you can invert and multiply. So I'm going to multiply the numerator and the denominator of this fraction by sine of theta, which cancels the denominator out, but the numerator is going to turn into sine squared theta. And this is going to turn into cosine squared theta. So we know this is identity, so this is equal to 1. So to simplify, you can still write it in terms of sine and cosine and look for a Pythagorean identity, so this is equal to 1, and write them all in sines and cosines. When you're solving a trig equation, you really want to read carefully about if you're solving for all the values or all the possible angles, or is there a boundary for the angle? And you also want to read if you're talking about in degrees or in radians. So if you read that it's theta, you're going to be speaking in terms of radians. So if I look at let's just do a simple one as the sine of theta is 1/2. So think of all the measures of theta in degrees, so all the angles with a sine of 1/2. So when we're looking at the unit circle right here, the sine is 1/2. Over here, the x value, or the y value, is positive 1/2. So those would be two solutions. Two solutions would be pi over 6 and 5 pi over 6. But I could keep going around. So I could have pi over 6 plus 2 pi, pi over 6 plus another 2 pi, another 2 pi. You could have 5 pi over 6 plus another 2 pi, another 2 pi. So you have to read if you're talking about a boundary like this problem or the infinite number of solutions. So when I'm solving this first one, what I'm noticing is that I can factor out a sine. So I write the sine of theta times the sine of theta, and then minus 1 equals 0. So I can use a zero product property and I can have two equations. One is the sine of theta has to be 0, and sine of theta equals 1. I added 1 to each side right here. I had this side equal to 0 and I added 1. So now I'm thinking of what are all the angles, or what are the angles between 0 and 2 pi, and including the endpoints where the y value is 0. So let's look at our unit circle. Where is the y value 0? Well, the y value is 0 at 0 radians, pi, and also 2 pi, because we could include 2 pi. So my solutions so far are 0, pi, and 2 pi. This is what theta is equal to. Now I'm going to answer the question, where is the sine of theta equal to 1? So where's the y value equal to 1 in the unit circle? Where the only spot is pi over 2. So here I have 4 solutions within the boundary of 0 to 2 pi, including 0 and 2 pi. So if it was infinite, if it was all solutions, then you'd have to add 2 pi n's, where n is the number of times you're on the circle. Next one, solve for all angles in degrees. So this time we're in degrees, not radians. So what I'm going to do is I'm just going to treat this like a regular variable, where I'm going to add cosine of x to each side. So cosine of x plus cosine of x is 2 cosines of x equals root 3. I'm going to divide both sides by 2, so I get cosine of x equals root 3 over 2. So in this case, you're trying to do, give me the angle with a cosine of root 3 over 2, all the angles in degrees. So where is the x value equal to root 3 over 2? Well, it's right here and right here. Cosine's positive in the first and fourth quadrant. So these in degrees, one answer is 30 degrees, but remember I need to keep going around the circle, so it's plus 360 degrees n. And my other answer is 330 degrees plus 360 degrees n. So a popular standardized test question is, if you know the sine of theta is 8/15, write the other 5 trig ratios. So you have this right triangle. It only works in a right triangle here. So if the sine of theta is 8/15, so we need to put theta someplace. It really doesn't matter if you put it right here or right here. So I'm going to put it right here. So remember, sine is opposite over hypotenuse. So 8 has to be the opposite, and 15 has to be the hypotenuse. So I write 8 on opposite and 15 as a hypotenuse. Write the other 5 trig ratios. So in order to do that, I need to figure out what this side is. So in a right triangle, I can use Pythagorean theorem. So 8 squared plus b squared equals 15 squared. 64 plus b squared equals 225 minus 64. B squared equals 161, which I don't think it can be broken down any further, so it's the square root of 161. So it's the square root of 161. So now I'm going to go through and write the other 5 trig ratios. I already have sine, so I'm going to do the cosine of theta. So cosine is adjacent over hypotenuse. So it's a square root of 161 over 15. The tangent of theta is opposite over adjacent, so it's 8 over the square root of 161, which you want to rationalize, excuse me, as this 8 root 161 over 161. And now I'm going to do the secant. This is kind of getting messy. So the secant of theta is the reciprocal of cosine. So it's 15 over the square root of 161, which rationalizes to 15 root 161 over 161. I need to do the cotangent of theta, which is the reciprocal of tangent. So that's the square root of 161 over 8. And I haven't done the cosecant. So the cosecant of theta is the sine, which was 8/15 reciprocal, so it's 15/8. The last thing you want to be able to do is go back to using SOHCAHTOA to find missing sides and angles. First what I would do is I would use the Pythagorean theorem. So to get this missing side length, I have 5 squared plus x squared equals 13 squared. But in this case, this is a triple, so it's 12. Now if you didn't know that shorthand, that shortcut, you could just do 13 squared minus 5 squared and you'd get 12 squared. So now I have the lengths, now I'm going to find an angle. So I'm going to find this angle. So in order to find this angle, I'm going to use the whole numbers on here, or the rational numbers. All 3 of these are rational. So I'm going to use cosine of these two. You could use the tangent. I could write 3 different ratios. I could do the tangent of x equals 12/5. I could do the sine of x equals 12/13. And I could use the cosine of x equals 5/13. You could also let this be y and change all your other ratios around. So in order to find the missing angle, to find angle measures, what you need to do is use the inverse. So I'm going to do the tangent inverse of 12/15 or 12/5. It's a 5. So on my calculator, I make sure you're in degree mode here. You can put tangent inverse of 12/5, or you can do sine inverse of 12/13, or any one of these, and it's going to give you the angle measure. So once you get this angle measure, these 2 angles have to add up to 90 because there's 180 degrees in a triangle, and this is already a 90 degrees triangle.